Yes, so we will start the session, Advanced Encryption and Signatures. The first presentation is public key encryption with flexible pattern matching by Elie, Bouscatié, Guilhem, Castagnos, Olivier Sanders. So please go ahead, Elie.
Thank you very much. Hello, everyone. So first, just to recall that classical public key encryption ensures the privacy of traffic between users. But if the receiver wants to use an intrusion detection system, so a service provider who analyzes the traffic to check if there is malicious activity, then he can only give the secret key to him, and it breaks the end-to-end encryption. So in searchable encryption, if the service provider needs to search for some pattern W, he can ask a trapdoor to the receiver, and with this trapdoor, he can see if the pattern occurs in the traffic, but he learns nothing else. Okay, so now what I want to show you is that the use case we are looking at is very different from the one of some existing solutions, namely symmetric searchable encryption. So if we compare the case where we are routing emails, emails can be associated with keywords naturally, like the words that appear in the object field. So they are indexable data and in deep packet inspection. So if we look directly in the traffic, it's like it's a stream that may or may not contain some pattern. So in the first case, the server who is looking for mails with some keyword is just performing an equality test with the keyword attached. And in our case, he's trying to find a pattern that can occur at any position in the stream. Here, the dictionary of keywords can be set before setup. But here, the patterns that are filtered evolve to get new virus signatures. And a pattern can even be searched in something that has been encrypted before we chose this pattern for forensic search, for instance. So we give another name to a special case, and we name it stream encryption, supporting pattern matching. So just a quick look at the kind of pattern that we can have to search. So this is a list for some version of Snort, which is an IDS, an intrusion detection system. And we see there are many patterns. And we see that they have very different lengths, quite short, but very different lengths. And so some solutions try to get back to string equality. So they break the stream into strings of fixed length. So for instance, here in blind box, if we choose a sliding window of 4 letters, every 4 consecutive letters will be encrypted into one ciphertext element, and we can give trapdoors for only keywords of length 4. So for instance, we can give a trapdoor for host, and the service provider can learn that host is in there. But hostile has a different length, and so it won't be encrypted at once, and we cannot give a trapdoor for it like that. So one possibility would be to encrypt everything for each length, but we have seen that the patterns have very different lengths, so this is very low efficiency. And a third possibility would be to break hostile into host and tile and to search these two. But now the service provider learns more information. He can learn if tile is in it. And we have seen that there are many patterns. So if we do that for every pattern, we get a lot of extra information for the service provider. the generic solution, we are not really interested in them because they are very costly. So we wanted solutions that are more specific to our problem. And there exist 2 papers that use bilinear pairings, and the second one is really adapted to streams, but they have 2 limitations. First, both of them rely on a very strong assumption that is interactive, and their public key depends on the size of the alphabet, and patterns use byte strings. So there is a 2 to the 8th factor. And so we address both this problem by providing 2 schemes. The first one is really efficient, and it reduces the size of the public key by a factor 2 to the 4th, and it halves the size of the ciphertext of the previous solutions. And the second scheme also has removed the dependency on the alphabet size, and it's the first one that uses a static assumption for security. Yeah, that's it for me. Thank you. Yeah, any question is welcomed.
Thank you. So no question on Zurip chat. If you have some question or comment, please write down on Zurip or Zoom chat. So I have one naive question. So what is the next direction or some open problem of your work here?
So the security that is proven for all these schemes is selective security. So we are looking for adaptive security if possible. And another thing is that we are using bilinear pairings, and it's still costly for real-time computation. So we are trying to find lighter solutions also. Yes.
Okay, thank you. So for adaptive security, so your scheme use bilinear pairing. So usually such kind of public key encryption scheme can be leveraged too by using dual system encryption framework. So you tried it already?
So yes, we are looking at these solutions, and so the first papers that we see, they don't provide directly a solution for it, because the security that we are using is the adversary can make a lot of queries for trapdoors in it. So it's at least very much more complicated than identity-based encryption or stuff like that. So we are looking for more sophisticated things, and we'll see if there is something that works. Yeah,
I see.
Definitely, that's a really nice way.
Yeah, very nice. Yeah, I see. I understand the technical hurdle. Okay, so any other question or comment? So we have no more comment. So
okay,
we turn to the next. So Jiahui Liu. So can you make a presentation here now? Huh? Oh, okay. So the next talk is title is Adaptive Security via Deletion in Attribute-Based Encryption Solutions from Such Assumptions in Bilinear Groups by Rishab Goyal, Jiahui Liu, and Brent Waters. So presentation will be given by Jiahui Liu. So please go ahead.
Okay, just give me 1 second. Okay. Okay, so I'll talk about adaptive security via deletion attribute-based encryption. And this is joint work with Rishab Goyal and Brent Waters. So
we
as
can
we
see the presenter view. Do you mind sort of just?
Really? Okay.
Yeah, just.
Yeah. Sorry. Let me share once again. Let me share. Okay. Is it good right now?
Good.
Okay.
Good.
Okay.
Nice.
Okay. Cool. Okay. So okay. As we know, AB was first formulated in these two papers, and in AB scheme, every user has attribute as MB binary string, and we have policies as Boolean functions. The two issue keys, we first generate the public key and master secret key, and we derive. And when we encrypt, we can using master secret key, we can derive secret keys associated with different attributes. And when we encrypt using the public key and policy. And only users with the secret key associated with attributes that these policies evaluate on them to be 1 can decrypt the ciphertext, and the rest cannot. And this formulation is called ciphertext policy AB, specifically since the policy is embedded into the ciphertext. And there's also dual formulation called key policy AB, where we embed the policy into the secret key. And both of these formulations, we have 2 levels of semantic security requirement. In most papers, will discuss these 2 levels. And what we usually would want in practice is, of course, the full security, also called adaptive, that the adversary first sees the public key, it queries a bunch of secret keys associated with some attributes, and then he sends in a challenge policy and two messages. The challenger encrypts one of the messages with respect to this policy, and the adversary is not supposed to guess which message is encrypted. This definition, even though natural, but it's in fact hard to realize in most cases, and people often turn to this weaker notion called selective security first, if they are not able to prove adaptive security. And in this case, adversary has to send in the policy, the challenge policy it wants to attack on before it even sees the public keys. If we look at the line of works that try to build a secure ABE, so starting from group assumptions, these early works built a selective secure ABE from bilinear Diffie-Hellman. And later on, there was this dual system technique introduced by Waters, and we could realize adaptive security, but the real reliance on decisional bilinear assumptions seems inherent in these works, in these techniques. And whereas the earlier selective secure schemes can actually be built from search assumptions. And moving to the lattice side, these works realize selective security from lattice, but it was always, it's been a long time before we finally had something of adaptive security from lattice. And there was a recent breakthrough in 2019 by Sabri. It realized adaptive secure ABE from lattice, even though the functionality was in fact a subset functionality. It is a step forward towards adaptive security, and it's different from our past approaches. And we therefore would ask, can we generalize this approach to make adaptive security hold for more general cases? Okay, in our work, we simplify and expand the framework of realizing adaptive security in Sabri 2019. And we show that the simplified framework can be instantiated from both search bilinear assumptions and lattices. And we still stick with the subset functionality. And our high-level approach is combining 2 building blocks. The first one is a selective secure key policy AB with deletable property, and it should for NC1 circuit. And the second building block is constrained PRF with this deletion conforming property. Together, we can realize adaptive secure and ciphertext policy ABE. And let's quickly go over the properties we need. So what's a deletable ABE? So basically, we have 2 approaches to perform deletion. The first one is we can remove certain blocks on the ciphertext according to an index set. And the second one is we remove certain indices in an attribute, replace it with like a special symbol, for example, bot, and we can have a valid encryption procedure that encrypts such a ciphertext, and we get a ciphertext that is indistinguishable from one that where we perform the deletion over the ciphertext. And a second building block is a constraint PRF. We know that in constraint PRF, we can constrain the secret key according to a functionality, so that you can only evaluate on the inputs that satisfy this functionality. And here we need additional property for the constraint PRF. Oh, sorry. We can actually constrain the PRF by just removing certain blocks from the master secret key, similar to what we did to the attributes. And here we can, given functionality F, we should be able to know which blocks we should remove. And another property is that we can do this evaluation on the PRF with some hard-coded X. And so due to time restriction, I won't go into talk about how we combine these two building blocks to give us fully secure ABE. Let's just briefly talk about how we instantiate these building blocks, and the audience can refer to our papers for the details on the construction. And to instantiate deletion conforming constraint PRF, it's not hard. We can have such a constraint PRF with a subset functionality following these two works. And for lattices, we have sort of more choices. For deletable ABE, we have more choices on instantiation. We can, for the bilinear group side, we can modify the GPSW 2006 paper, the one using a search assumption, and we can turn that into deletable. And for the lattice side, we can turn both of these two constructions into a deletable ABE scheme. Even though some of you might know that there was recently an attack on the Boyne 13 scheme, but the attack came out after our first draft, and we still leave the example in our paper as just for illustrative purpose on how deletable ABE works. And finally, there's also concurrent work by Katsumata, Nishimaki, Yamada, and Yamakawa that extend the functionality of subarray scheme into inner product. And that's everything for this talk. Thank you.
Thank you. So any question or comment? I cannot find any comment or question on Zurip or Zoom chat. So I have one naive question. So comparison with recent Katsumata et al.'s work, your work, what is a main advantage of your work compared with their work?
Yeah, we expand the framework of the subarray scheme. So in subarray scheme, it's using this very specific properties of it. Like overall, it's using this. It's just perfectly over working with the BGG plus 14 lattice-based construction. But in fact, we can abstract the properties out. And it is actually a more generalized framework with like certain ABE and certain constraint PRF, and for that kind of ABE, we can actually fit some other existing ABE schemes into the framework. And I think for the Katsumata et al. Work, and they do expand the functionality, but they sort of follow this very specific lattice-based construction as in the subarray scheme. So yeah, it's not a very abstract. It's like a more like non-black box use extension of the work, right?
Yeah, I see. So one advantage is security from computational program. Yeah, okay, thank you.
Yeah, yes. So we can have we can have security from computational group assumptions, and right.
Okay, so any other question or comment? So no comment. Thank you very much. And
okay, thank you.
Please
okay, I'll stop share.
next talk. Next talk, the title is Bounded Collision ABE for Turing machines from IBE. The authors Rishab Goyal, Ridwan Said, and Brent Waters. So Rishab will give a talk. Go ahead.
Thanks a lot for the introduction. And yeah, today I'll tell you how to build attribute-based encryption for the uniform model of Turing machines from a general assumption of identity-based encryption in the bounded collision model. So just let me quickly recap attribute-based encryption. So Jiahui did a great job of telling you about attribute-based encryption, but I'm going to be switching things around a little bit. So let me just redo it again. So attribute-based encryption is a fine-grained notion of encryption which allows fine-grained access of over encrypted data. So it can be pictorially listed using the following picture where we have two parties, Alice and Bob, where Alice has some private data M and it wants to share this private data M corresponding to the people who satisfy certain attributes. So Bob has a secret key, Alice has a public key, and Alice basically encrypts her message under these attributes. Now, suppose we have a third party, Charlie, and Charlie here, it wants to recover the message M as long as the policy that Charlie has, it satisfies the set of attributes. The attributes could be, I am, say, age, people over age 25 can decrypt this particular ciphertext. So that's one example. And one way to solve this problem in order to enable Charlie from decrypting this particular ciphertext, Charlie can simply send the ciphertext over to Bob, and Bob can decrypt the ciphertext, authorize whether check whether Charlie is authorized or not, and send it back. But this is not very efficient because you have to perform interaction. Attribute-based encryption allows a non-interactive and a very efficient way of solving this problem in which you can come up with some partial secret keys called predicate secret keys for a function f such that given this predicate secret key, you can perform decryption on its own. So the advantages of attribute-based encryption is that it allows this fine-grained access over encrypted data. You can choose when to release encrypted data, and it solves this problem without outsourcing, and even when Bob is offline, Charlie can perform this decryption. So a little more abstractly, as you already saw in the previous talk, we have a setup algorithm which generates the master set of public and secret keys. Using the master public key, you can encrypt any message for the attribute string of your choice. Recall, I'm switching the attributes and policies. In the previous talk, you saw policies being encrypted in the ciphertext. Here, I'm going to talk about attributes being encrypted under ciphertext. So it's like a dual version of which is called the key policy version of attribute-based encryption. So that means in the key generation algorithm, we take as input a policy and gets a secret key. And finally, we can combine the ciphertext and secret key to recover the message depending upon whether the policy was satisfied or not on that given attribute present inside that ciphertext. And for security, as you saw, typically the intuition is that the adversary should not be able to learn anything beyond that it can learn by performing decryption. So suppose adversary is given a ciphertext and a bunch of polynomial secret keys. As long as none of the secret keys, none of the policies associated with secret key can satisfy the underlying attributes, the message should be hidden. If you can satisfy the attribute, then you can run the decryption algorithm, learn the message. Otherwise, it should be completely hidden. And what's more interesting about attribute-based encryption is that attribute-based encryption really depends upon the class of policies that you can build it for. If the class of policy is just empty, then it's basically the public key encryption. But depending upon how explicit the class is, you get more interesting applications. Typically, the models of computation that has been discussed or have been studied so far for attribute-based encryption can be split into two categories, the non-uniform and the uniform classes. With the non-uniform classes, we have Boolean formulas and circuits. But the problem with that is that the attributes that you can encrypt have to be of fixed size. You have to declare that this is the length of my attributes. Whereas in the uniform classes, such as deterministic finite automatas, Turing machines, RAM programs, etc., you can handle potentially unbounded length attributes. So basically, the main difference is that in the non-uniform setting, you have a separate key for different length attributes, whereas in the uniform classes, you have one single key that can decrypt potentially ciphertexts that encrypt different varying length attributes. So in practice, uniform model of computation is much more useful for attribute-based encryption. And so far, we've seen that there has been tremendous amount of progress in trying to build attribute-based encryption from a wide variety of assumptions such as bilinear maps, learning with errors, multilinear maps, and much more. And one commonality for all these positive results is that they require specific algebraic assumptions to enable attribute-based encryption. And even further, there seems to be a gap between the feasibilities that we have for the non-uniform models as well as the uniform models. Typically from the non-uniform models, it's easier to use algebraic assumptions to get feasibility results. But for uniform models, we still don't know a lot. For example, we don't know how to get collision-resistant attribute-based encryption for say Turing machines in the from a standard assumption. If you don't want to go via the route of obfuscation, for which we have constructions from well-founded assumptions. But going forward, the question that we ask in this work or under consideration is that, is there always a gap between uniform and non-uniform models? Or can we actually get the same feasibilities for the uniform models as well? And in general, can we also rely on general assumptions, non-algebraic assumptions to perform this instantiation? And in this work, we show exactly the following. We build an AB scheme for Turing machines, which is a uniform class, from identity-based encryption, which is a general assumption, in the bounded collision model. And the two theorems we show in this work is that starting with IB, you can build a non-adaptively secure AB scheme with Q collisions. And you can also upgrade this security to adaptive security if you if you work in the random oracle model. And one caveat of our results is that although the encryption algorithm can take as input unbounded length attributes, the runtime of the Turing machine that can be run on those attributes has to be declared during encryption time. So the attribute length is unbounded, with the Turing machines, which you can run on that particular attribute, that has to be a priori bounded. And as a consequence, we also were able to propose a fine-grained simulation security for something called garbled RAMs, as it was an important ingredient in our construction. Now, just trying to explain our result a little bit better, let me explain what the bounded collision model is. Let me just recall it. So this was the security definition that we saw before. The bounded collision model says that the security holds as long as the number of corruptions of keys that the adversary can do is bounded, is at most some a priori decided parameter Q. And as long as you don't corrupt more than Q keys, the security still holds. And although this is weaker than fully collision resistant model, it is very interesting and has seen many interesting applications. And it turns out in the landscape in the bounded collision model is already very interesting. For the non-uniform models, we already know that AB for circuits can be built just from public encryption, the minimal assumption. But it turns out all prior constructions for AB, for any uniform models, even in the bounded collision setting, they need specific algebraic assumptions. So there's a huge gap for non-uniform models, just public encryption is enough. But for uniform models, it's not clear. And in this work, we precisely show that algebra is not needed for uniform models, and you can start from general assumptions if you're working in the bounded collision model. So at a very high level, our construction for attribute-based encryption proceeds in 3 steps. In the first step, we design an attribute-based encryption scheme for Turing machines, in which we only allow one single key corruption. The second step, we show how to go from single key corruption to bounded key corruption. And then we show how to upgrade non-adaptive security to adaptive security in the random oracle model. So combining all these things, we get both of the results. And due to lack of time, I won't tell you exactly how to do it, but let me just quickly summarize. So the step 2 follows by standard combinatorial tricks for amplifying collision bound. But as in the third step, we rely on a very simple non-committing encryption scheme that we instantiate in the random oracle model and show that this particular non-interactive non-committing encryption scheme can be used to upgrade security. Now, the step 1 is where a lot of technical ideas came in, and in the interest of time, let me just summarize them very briefly. So the intuition is as follows. To build an AB scheme with one single key corruption, we work as follows. The ciphertext is going to contain T garblings, where the T is a time bound of the Turing machine that can be run on this particular ciphertext. Each garbling is going to perform a computation step of the Turing machine. So the ith garbling is going to perform the ith Turing machine step, and it's basically going to output the labels for the I plus 1th garbling. And the labels are actually encrypted under certain identities, which correspond to the Turing machine transitions when you go from the ith step to the I plus 1th step. And the secret key for a particular Turing machine is going to be the identity keys for the IB system for the appropriate Turing machine state transitions. Basically, during decryption, I will run the first garbling. That's going to give me an encryption of the wire labels for the next garbling. And those encryptions can be recovered depending upon my state transitions. That's the high level idea. And I invite you to look at the full version of the paper or just the full paper to see how we execute this. but just throwing in a little more of details, what type of gobblings do we need? So it turns out gobble circuits could be enough, could be sufficient, but they lead to quadratic blow up in the ciphertext size if you just use them naively. And we show that using gobbled ramps, we can make it linear, much more efficient. And the point is that in gobbled ramps, we have a persistent memory database, and we have different RAM programs. So that's why we can take out this RAM, this memory, to encode the database, to sort of encode the Turing machine state. In gobbled circuits, you have to pass this Turing machine state during each RAM program, which we try to avoid. And in this paper, we propose a new security definition for gobbled ramps, which we call iterative simulation security. And basically, the point is that in the standard notion of security, all RAM programs for the given database have to be simulated together at the same time. But in this work, we show that the simulation still works if you simulate the programs, some of the programs, and compute the rest of the programs honestly. Then still we can get interesting simulation security properties. And this is very crucial for our proof, since we have to simulate things step by step, and we can't simulate things all at once because we work in this unbounded model, unbounded attribute model. And yeah, just please look at the paper for details. And trying to conclude, in this work, we provide the bounded collision attribute-based encryption scheme for Turing machines from IBE. And we provide security in the adaptive and non-adaptive setting in the random oracle and the standard assumptions. And this is the first uniform model attribute-based encryption scheme in the bounded collision setting from general assumptions, which does not rely on algebra, showing that the gap between non-uniform and uniform is actually is not that big, at least in the bounded collision model. And we also provide a new finding simulation security for gobbled rams, which we show can be instantiated from prior works by a new security proof. And just trying to conclude with some interesting directions for the future work, a very natural question could be, can you actually do the same for functional encryption? Can we get functional encryption for Turing machines in the bounded collision model? Or can you also remove this time bound that we had in the encryption algorithm? And can we go beyond, can you prove adaptive security without relying on random oracle models? And recently there has been some other bounded collision models, which are called the dynamic collision bounded model. Can we actually extend our results for AB for Turing machines in those dynamic model as well? With that, I would like to conclude, and thanks for listening, and I'd be happy to answer any questions.
Okay, thank you. Very nice talk. So any question or comment? I cannot find. So I have one naive question. So you say at the end of your talk, the challenge is to leverage to adaptive security without random oracle model. And I think in the uniform computational model, Turing machine, so maybe selective, the gap of selective security and adaptive security is more large, and because that in the key policy type ABE, so the main advantage is any length attributes can be handled, but if selective security, we consider selective security, so as the first of the game, we should declare the challenge attribute. So maybe the hurdle is very get low compared to the non-uniform model. So maybe the hurdle is large, gap is large. Is it right?
So that's a great question, Katsuyuki. But it's possible, but I don't think that might be the case. The reason is the following. The reason is that even right now, we prove something stronger than selective security. We prove non-adaptive security. In non-adaptive security, the only restriction is that there should not be any post-challenge secret key queries. So you do not have to declare the challenge attribute at the beginning of the game. All you have to do is that the secret key queries must be made before seeing the challenge ciphertext. So you actually don't need any information about the challenge ciphertext. The property is that we have to hardwire certain computation inside the challenge ciphertext, and that's why we need to make those queries before. So I think this is, I haven't spent too much time on it, but I suspect that we should be able to use tricks from the adaptive security of gobble circuits literature, where we use these pebbling techniques to prove adaptive security. And I think those techniques have already been used to prove adaptive security for ABE in the Bilinear map literature. And I think those ideas can also be used to prove adaptive security by a more fine-grained analysis of our construction, because we right now work in a lot of these abstractions. If you open up all the abstractions, do everything from first principles, and have a very, very fine-grained proof where you use these pebbling structures, pebbling tricks in a nice way, I think you should be able to get to adaptive security as well. I'm not saying it's immediate. I think it's feasible, but this needs to be more research done in order to solve that problem.
Okay, okay. Thank you. Very interesting. But we have no time. We should switch to the next talk. Thank you very much. Yeah, please to the next talk.
So I will chair the next three talks. This is Xinyi Huang from Fujian Normal University, China. Our next talk is digital signatures with memory-tied security in the multi-challenge setting. And it will be presented by Ning. Ning, are you here?
Yes, yes.
Okay, great, great. It's your time. Yeah.
Okay, yeah. Hi everyone. My name is Ning Liu, and I'm glad to briefly introduce our work, digital signatures with memory-tied security in the multi-challenge setting to you. And in our work, we consider memory-tied reductions. Researchers usually measure the quality of a reduction via its running time and success probability or advantage. Albert et al. They observed that memory is also a valuable computational resource and should be considered as a measurement for reductions. So they call a reduction memory-tied if the overall memory consumed by the reduction is approximately the same with the memory consumed by the adversary, and especially independent of the adversary. And one interesting setting in this direction is that is the multi-challenge a strong UF-CMA security or the MS-UF-CMA security of digital signature scheme? Different from classical single challenge security, the adversary could submit multiple forged queries throughout the MS-UF-CMA game and wins if at least one of the forgery is valid. And without considering memory, single challenge security tightly implies the multi-challenge security. However, Albert et al. And Huang et al. Shows some impossibility results for MS-UF-CMA security when memory is considered. They show that certain black box reductions from multi-challenge security to single challenge security or to some computational problem must be non-tight with respect to memory or time. So our work shows some good news, and we focus on finding which properties of reduction are sufficient to achieve memory tightness. And keeping the impossibility results about black box reductions of Albert et al. And Huang et al. In mind, we decided to consider non-black box reductions and on a weaker security notion, which we call the CMA1 security. And even in this setting, we still face the main challenge that the reduction needs to distinguish fresh forgery from replayed message signature pair without using memory. So our first step towards solving this problem is that we define a special kind of non-black box reduction, which we call the canonical reductions. And the idea of a canonical reduction is that the reduction R deals with a single challenge adversary A and simulates a signature for A in some deterministic way. And then the check for the final forged query can be done by comparing the sigma star with the simulated signature for the message M star. And in this way, the reduction R does not use memory to store any signature message signature pair. However, canonical reductions are still restricted in many aspects. For example, it only deals with single challenge adversaries, and it is still not memory tight because it needs to simulate a random function. And it only works for a weaker security notion, which is the CMA1 security instead of the normal CMA security. And despite of these restrictions, we are able to use canonical reduction together with a memory-tight pseudo-random function to show a good results. More precisely, if there is a canonical reduction R, which proves that some signature scheme sigma prime has SUF CMA1 security, then we can build another reduction R prime, which proves that sigma prime has memory-tight MS-UF-CMA1 security. And this result is nice because we can go from single challenge setting to the multi-challenge setting memory tightly. However, we are still in the CMA1 security case. And to upgrade the security from CMA1 to CMA, we take our second step. More precisely, we choose an additional nonce of length 2 lambda and sign it together with the message. We are able to show that the new signature scheme is MS-UF-CMA secure if the original signature scheme is MS-UF-CMA1 secure. And this transformation also preserves memory tightness. So we achieve our goal via these 2 steps. And to instantiate our approach, we only need to construct signature schemes with SUF-CMA security and show some canonical reduction R for such schemes. And we are able to instantiate our approach and get concrete memory-tight MS-UF-CMA security to signature schemes. As you can see in this table, we get 3 fully tight signature schemes. By fully tight, we mean that they are tight in terms of memory, time, and advantage. And the 3 of them are a lossy identification-based digital signature scheme, and a variant of the RSA full domain hash scheme, and a variant of the Boolean-Lin-Schachtman scheme. And the cost to achieve full tightness is a 2 lambda expansion in the signature size. And to summarize our work, we propose a generic approach in getting a memory-tight MS-UF-CMA signature scheme. And we instantiate our approach and get 3 digital signature schemes with fully tight MS-UF-CMA security. And our results do not conflict with the impossibility results by Abel et al. Or Wang et al. Because we can circumvent these lower bounds since we focus on a special kind of non-black box reductions, which we call canonical reductions. And a limitation of our work is that the memory-tight signature scheme we consider, regardless of fully tight or not, are proven in the random oracle model. So we think getting a memory-tight multi-challenge secure digital signature scheme in the standard model is an interesting open problem. So that's all for my talk. Thank you very much. I'm happy to answer any questions.
Thank you, Lee. So any questions for the speaker? Okay, let me check. Okay, so I have one simple question. It is about the practical meaning of this kind of digital signature. So, which kind of scenario would need this digital signature secure in the multi-challenge setting? Could you give me a very simple example?
Yeah, thank you very much. And I think practically, the number of forged queries for a practical adversary is unbounded. The adversary could always try to forge signatures. And a single challenge security, without considering memory, single challenge security tightly implies the multi-challenge setting. And I think memory tightness has some impact for practical usage because in practical world, the number of forge attempts by the adversary is unbounded.
Okay. If there's no more questions, so thank you, Lin. So we'll go to the next talk. Okay. The next paper is compact adaptively secure FE for attribute weighted sum. And the speaker is Tapas. Okay.
Hi everyone, I'm Tapas from IIT Kharagpur. I'll be presenting our paper, Compact Actively Secured FE for Attribute Weighted Sums from Guilhem. This is joint work with Potis Datta from Entity Research. So in function encryption, there is a setup authority who generates a master secret key and a master public key. Using master public key, one can encrypt a message M and computes the ciphertext CT. Now a decryptor who wants to decrypt the ciphertext CT queries for a functional secret key corresponding to this function F. And the central authority will now compute a secret key SKF using the master secret key and gives this to the decryptor. so that the decryptor will now decrypt the ciphertext city and learns function of the message and nothing else. So in this work, we construct functional encryption scheme for attribute weighted sum functionality introduced in AGW20. So in such a scheme, message is divided into two parts. One is the public part, first one, which is xi, and the second one is gi, which is the private part. So the functionality is as follows. The function of the message m is equal to summation over I if xi transpose gi. And now say this I is not a priori bounded in the setup, then we call it unbounded slot scheme. So to get an idea about the importance of this sort of functionality, I will discuss some special cases. Suppose if outputs a fixed vector, then it will imply inner product function encryption or IPFE. And if Z is a payload and F is a Boolean function, then it will be attribute-based encryption. And thirdly, if fx is of the form y times gx, then it will be attribute-based inner product function encryption recently explored in ACGU20. So in AGW20, they proposed FE for attribute-weighted sum functionality with some interesting features. The first one is that their scheme support unbounded slot and the weight functions are ABPs or arithmetic branching program. And their ciphertext size depends only on the size of the private part of the message. And the security is based on Kalin or MDDH assumption, which are known to be standard assumption. However, they prove security only in the semi-adaptive simulation security model. And we know that it is not a realistic model. So it seems that C-selective security is weaker than semi-adaptive and semi-adaptive is weaker than adaptive security. However, due to GKW16, selective security is kind of equivalent to semi-adaptive security. And the known transformation from semi-adaptive to adaptive security requires the underlying semi-adaptively secure functional encryption to support general functionality. So due to this fact, AGW20 posed an open problem in their paper to construct FE for attribute-weighted sum functionality with unbounded slot for ABPs with compact ciphertext and adaptively simulation security based on standard assumptions. So before going to discuss our work, let's see some previous works and challenges in solving this open problem. So on the right-hand side, sorry, in the left-hand side of the scheme, we see that some of the existing ABEs, which are presented in the context of partially attribute hiding setting. First two schemes are semi-adaptively secure, whereas the last one by DOT80, they were able to prove this adaptive simulation security for where the policies are ABPs. And in the right-hand side, we see some functional encryption schemes for different functionalities. The last two FEs are semi-adaptively secure, whereas the first one is adaptively secure only in the indistinguishability-based model. And lastly, in a series of work, we see a functional encryption scheme for inner product functionality, which is proved secure in the adaptive simulation-based security model, and it supports unbounded collision. So what you can see that is that achieving adaptive simulation security with unbounded collision for functional encryption is really a challenging task. And till now, I think we know it only for linear functions. So in this work, we present adaptively simulation secure function encryption scheme for attribute-weighted sum functionality, where the weight functions are ABP. First, we present a one-slot scheme, then we convert it to an unbounded slot scheme with a small caveat, which I will explain in the next slide. Our scheme support complex ciphertext, meaning that the ciphertext size will not grow with the multiple occurrence of a particular attribute in the weight function. And also, the security is based on standard Kalin assumption. And from the technical ground, we extend the LL20 framework from ABE to FE. That means from payload hiding to partially attribute hiding setting. So I will now discuss a very high-level overview of our FE scheme. So we consider two cryptographic tools. First one is the arithmetic key garblling scheme, in short AKGS, which is an information theoretic tool, and it is a particular type of randomized encoding. And the second one is function hiding inner product function encryption, which is a computational tool, and in short I will call it IPFE. So firstly, using AKGS and IPFE, we construct a one key, one ciphertext secure, one slot, one FE scheme in the secret key setting. And then we convert it to a full-fledged one slot FE scheme in the public key setting. However, for that, we require slotted version of the IPFE. Next, we convert our one slot, one FE scheme to a one slot, one EXT FE scheme, which is again in the secret key setting, and it supports single key and a single ciphertext. So what is the XTP functionality? So in this functionality, secret keys are generated for a function f and a vector y, and the ciphertext is computed for a public vector x and two private vectors a, z, and w. And during decryption, we learn fx transpose z plus y transpose w. The next step is to extend this one slot one EXTF scheme to a full-fledged one slot EXTF scheme. And the idea that we have used is the same as the idea that were involved in the previous transformation. That means we need slotted version of the IPFE. And finally, we use the transformation of AGW20 with a little modification to convert the one slot EXTF scheme into an unbounded slot scheme. In our one slot EFE scheme, adversary can query any polynomial number of secret keys both before and after the channel ciphertext. However, in the unbounded slot scheme, the adversary can query only a priori bounded number of ciphertext before the channel ciphertext. However, after the channel ciphertext, it can query any polynomial number of secret key queries. So yeah, so this is an open problem to construct this unbounded slot scheme with poly security in the adaptive security model. Thank you, and for more details, please look into our paper. And yeah, I'm open to any question.
Thank you. So do we have any questions for the speaker?
So the Julie, is there any question?
Okay, so I got one question for you. So talking about the performance of the algorithms, do we have you ever done some experiments to run the algorithm on the normal PC? How is the performance of your design? Yeah,
this work is completely based on bilinear pairing, and I haven't done any sort of implementation, so I will not be able to tell how much runtime is and all. Yeah.
Okay, that's fine.
So this is completely theoretical work. Yeah. I haven't done any implementation.
It works from the point of view of theoretically, right?
Yeah.
Okay.
That's right.
Okay, thank you, Simon.
Okay.
We will move to
the
next talk. Okay, so our next talk is boosting the security of blind signature schemes, and the speaker is Michael. So, Michael, could you please share the slides? Michael, are you here in the room? Okay, is Michael here? Boosting the security of blind signature schemes. And the speaker is Michael Rosenberg. Is Michael here?
He appears not to be here.
Yeah. So, shall we close the session or shall we keep waiting?
We could wait a couple minutes, but
okay.
I don't think he's been here at all. And I think he's on the East Coast, so it would be 7 a.m.
Okay.
I think it's unlikely he's going to show up. Perhaps it's best just to close the session then.
Okay, so I think we have done the job. So this is a session of the advanced security and digital signatures. Yeah, thank you all.